All right, today we're going to talk about titrations and the many types of calculations and concepts that go on. Now, even though we've done titrations back in Unit 3, they're actually far more complex than we kind of let on. That's because we looked at it from only certain perspectives while we were back in Unit 3. So we're going to cover all angles today, hopefully, and we'll do a lot of practice problems in the next coming days. So, first, most titration problems, essentially, they're a stoichiometry problem mixed with an equilibrium problem, right? And because we covered stoichiometry and we covered equilibrium, you now have the ability to work through an entire titration calculation. We're going to evaluate three types of reactions: a strong acid, strong base, a strong acid, weak base combination, and a strong base, weak acid combination. So notice that in all combinations, there is at least one strong species present. All right. There are combinations of weak acid and weak base, but they're outside the purview of this course. Okay. All right. So definition of a term. We've used this term before, the equivalence point. And we define this as when your moles of acid and the moles of base are equal. Right? When the moles of the acid and the moles of the base are equal, that is what we call the equivalence point. Okay, and that term is going to come up again. So let's start with the type of calculation as review that we did back in Unit 3. So let's say that we are titrating 50 milliliters of a 0.1 molar HCl solution, and we're doing this with a sodium hydroxide solution. What is the initial pH? Calculate the pH after the addition of the base. Okay. So the initial pH of the acid, what that implies is if you just imagine your experimental setup, what they're saying is that you have your acid down here in the beaker, right? And so actually, it's titrated with. Yeah, okay, it's titrated with. So here's your burette. Bless you. So the NaOH is in here. And what we know that is, we know the volume. This is 50 milliliters. Ooh, it's very precise, 2 decimals. And we know the molarity. So the first question is, what is the initial pH of the acid? Well, the initial pH is going to be based on the concentration of H+. And because this is a strong acid, the molarity of HCl is the molarity of H+. So all I have to do is simply take the negative log of the concentration of HCl, but because I taught you a pattern the other day, we don't even need to calculate it. Can't you just look at this and tell me what the pH is going to be? Remember, the pH of concentration of 1 molar is 0 pH, so what's the concentration of 1/10 of 1 molar? Just give me 1. Just give me 1. All right, negative log 0.1, 1. All right, so that is the pH of our solution. Calculate the pH after the addition of the base. So remember that titrations typically end when we get to the equivalence point. And the equivalence point is when your moles of acid and moles of base are equal. So the first thing I need to do is figure out how many moles I have, right, of the HCl, because I know both the molarity and the volume. That is the first thing that I can calculate. So 0.1 mole per liter times 0.05000 liters. All right, so 0.00500 moles. That's how many moles of HCl are present. And because of the stoichiometry, with strong acid, strong base, oops, no, only one way arrow. Everything's 1 to 1. You know what? I should mention, with a strong acid, strong base reaction, a lot of times it's just the net ionic equation is used. So you will see this, and you can use this, right, if the stoichiometry is right, meaning if it's 1 to 1, this is the reaction that you will see. So hence the mole ratio of 1 hydroxide to 1 H plus makes sense. Okay. So if that is the number of moles of hydroxide at the end, at the equivalence point, at the equivalence point, your moles of acid and your moles of base equal each other, right? Which means they neutralize each other completely. So if they neutralize each other completely, then what do you have at the end? Water, salt water, right? And if they neutralize each other completely, that means you just have water, and if you just have water, this is what is happening. And do you remember if Kw is 1 times 10 to the minus 14, your H plus and your OH minus concentrations are equal? But they do have a value. You guys remember what that value is in plain water? What's the concentration of H plus or OH minus? Right, take the square root of 1 of Kw, correct. Right, and to justify that, Kw is equal to this, right? So if this is this value, what is the value of both H plus and OH minus? It's 1 times 10 to the negative 7. So if I said, what is the pH now after the acid and base have neutralized each other, you would take the negative log of H plus, which is 1 times 10 to the minus 7. Therefore, your pH would be what? Yeah, 7. Okay, technically, this is what is happening during a strong acid, strong base titration. And hoping that makes sense, both stoichiometry-wise and reaction-wise. Okay. So, let's talk about the different types of endpoints that we can see during different types of titrations. By the way, let's differentiate here. Here we have a new term. Endpoint is not the same as equivalence point. All right, endpoint is when the pH, when indicator, hold on a second. You know what? Actually, here, this is what I'm going to do. We'll talk about endpoints a little bit later when we talk about indicators. So I'm just going to scratch this out and say, instead of calling this the endpoint, let's call this the equivalence point. Right now, that's going to make more sense. Okay, not endpoint. We'll talk about endpoints later. Okay. Let's look at some different combinations. Over here, this would be a pH curve, and you have created this curve when we use the lab quests during our titrations. Right? You titrate. You have a low pH initially if you put the acid in the beaker, and then there's going to be a sharp jump, and then once you kind of get to the top shelf portion of this graph, the pH changes minimally at that point, right? So this is a characteristic S curve. And the things that you need to note about a strong acid, strong base titration is that this combination has the widest pH range. Can you even read that? Sorry. Let me read that. Widest pH range. Because if you look at this, your range starts at about 1, and it ends, if you kept on going, it ends at about 13. Okay? That's a wide range. The second thing, and quite possibly the most important thing about a titration curve with strong acid, strong base, is that your equivalence point pH is at 7. The equivalence point is found a couple of ways. Here it's the midpoint of the vertical stretch, right? The midpoint. It's kind of hard to judge the midpoint of a straight line, and that is why when we were carrying this out in lab, what we did was we took the derivative. You guys remember that? We took the first derivative, and when we did that, like if I were to do that over here in the same color, your derivative would look like this, right? And the inflection point of the first derivative, that peak, that is the volume that corresponds to the volume that would be used in calculating the molarity, right? Okay, so the equivalence point pH is at 7 if it's a strong acid, strong base combination. Also, the third thing you should notice, I'll number these, 1, 2. The third thing you should notice is that the lines are relatively rigid. They're relatively flat and straight. Okay, meaning this line here is relatively straight, this line here is relatively straight, and this line here is relatively straight. Think of it as 3 lines. There might be some curvature to it, but compared to all other curves, this is going to appear to be the most rigid. Okay? If this were a strong acid being added to a strong base, the curve would look the same. It would just be reversed because your pH starts high. Okay, so does that make sense, guys? If I did this again, it would look like this. But the same principles would apply. Your pH, your equivalence point pH would be 7. You would have sharp lines, and you'd have a wide pH range. Okay. So that is the first type of pH curve and the characteristics that you need to know about it. Let's look at a second. Weak acid with strong base. Okay, weak acid with strong base. So in this situation, you need to evaluate those 3 characteristics that I just mentioned and see how they compare in this situation. How's the range, how's our pH range here compared to the first one? Yeah, narrower, right? Your pH range is roughly that wide. Okay. Then your equivalence point is above 7. In this particular graph, our equivalence point is at a pH of 9. And so to explain that, we need to evaluate what we know about salts and about certain acids. So let's say that my weak acid that I'm using, let's just say fluoride. Let's say that I'm using HF. So here's the reaction. HF plus NaOH. Okay, so HF is my weak acid, NaOH is my strong base. So the products are going to be water and NaF. Okay? Now, what you should know is that NaF is a salt, but from our discussion of salts the other day, that ion, the ions that are produced here are going to be Na plus and F minus. And we talked about what certain ions would do in solution. What would a negative ion like F minus do? Yes, right. It's a negative ion. This is going to undergo hydrolysis, and it's going to be a basic reaction. So F minus, reacting with water, would end up forming hydroxide because the F minus ion is a basic ion. And that is why our pH here, when the moles of acid and base are equal, you end up with only the products, and it turns out that one of your products is weakly basic. That is why the equivalence point is above 7. Okay? So, the curve, the actual curve itself, notice how it's kind of wavy, right? More curvy linear as opposed to kind of rigid lines. So compared to a strong acid, strong base combination, you expect it to look like that. But really the main things, equivalence point above 7, right? That's kind of the main way you judge pH curve. Also, when we talk about narrow pH range, what is the initial pH? Because if your initial pH starts here at like 3.7, like this one does, it's not possible for you to have a strong acid with your pH of 3.7. At least not with standard labs. Okay. Hopefully that makes sense. Let's look at the strong acid weak base combination. So I'm starting with a weak base, which explains how my initial pH is around, 10, 11-ish. Right? And it's curvy. We have a narrow range. Your equivalence point aligns to a pH which is less than 7. Let's discuss why. So, most common weak base is ammonia. Ammonia being titrated with a strong acid like HCl. What do we get? We get ammonium chloride, but of course ammonium chloride ionizes, and it's the NH4 plus that is of interest here. NH4 plus is an acid. It donates its proton to form hydronium. So when the moles of NH4 plus, or of ammonia and HCl are equal, this is what we produce. What we have produced is a weak acid, and that is why at the equivalence point, the pH is acidic. All right. 3 types of titration curves, guys. Does each one make sense? You need to know why the equivalence point pH is what it is. And that is going to be your major clue as to what happened during that titration. Okay? If equivalence point pH is above 7, right, that means you had a strong base with a weak acid. If the equivalence point pH is below 7, that means you had a weak base with a strong acid. And if your equivalence point pH is at 7, that was a combination of a strong acid and a strong base. All right. So I guess the term didn't come up here. Let's define. Oh, here it is. Endpoint. So let's define endpoint. Endpoint and equivalence point are not the same. The equivalence point is when moles of acid are equal to the moles of base. The endpoint is when the indicator changes color. And whichever indicator you use, lots of indicators change colors at different pHs. So the two terms are not the same, although they might be confused to be the same. All right? So what's more important is the equivalence point. The endpoint is very qualitative. Endpoint, like, if you're using bromothymol blue, if you're using phenol orange, it changes. Okay. So now that you are familiar with types of titration curves, let's go a little bit deeper and talk about a specific part of a titration curve. There's a part of a titration curve called the buffered region, and we need to discuss what a buffer is. So first, the simplest definition of a buffer is that it is a mixture of a weak acid and its conjugate base. All right, so a weak acid and its conjugate base, any weak acid. So, for example, acetic acid, which is HC2H3O2, and something like sodium acetate, NaC2H3O2. This is the weak acid. This would end up being its conjugate base. Now, the sodium, of course, is inert. Really, what's important here is not the sodium, it's the C2H3O2 minus ion. That is the conjugate base. But the point is, whatever your weak acid is, you have to have its counterpart present at the same time. Now, this also works secondary. The other definition from the base perspective is it simply could be a mixture of weak base and its conjugate acid. That is also a buffer. If you have the conjugate pair in solution, that is a buffer. Whether you start with the weak acid or you start with the weak base. All right, so an example of this, like we said before, would be ammonia and ammonium. Okay, you guys clear on the definition of a buffer? You need both parts. All right. So, what is the significance? What does it do? So, buffers are solutions which resist pH change. They resist pH change, and this is very important. This is very important in industry and engineering, and for a lot of reasons, because the most direct example, think of eye contact solution. How many of you guys wear eye contacts, right? You know that, you have to clean them in a certain solution, and even before you put a contact in, sometimes you put drops on it before you put it in, just for comfort, right? The buffer in that solution, you have compounds that will neutralize acids and bases so that the pH of that solution is the same. Because if the pH changes, your eye becomes irritated, and it starts getting itchy and red, and you can't wear the contacts anymore, right? Your skin tissues actually, there's a certain pH for a comfort level, and if it varies from that, then you have irritations. If it gets too far away from that, then it could do some damage. So, example: if I have a buffer system, notice that I have in this case both B- and HB. So I've got a weak acid and I have its conjugate base. So the reason why you need both is because if the buffer encounters an acid, then the acid is immediately reacted with the conjugate base and neutralized. Right, the H plus, because think about what affects pH. It's H plus concentration. So if H plus is added, the H plus is immediately neutralized, and you end up forming HB. What if base is added? If the base is added, the weak acid neutralizes it to form water and B minus. So a buffer can handle incoming acid or incoming base. That is its purpose, right? And if the H plus is immediately neutralized, if the OH minus is immediately neutralized, then the concentration of H plus and OH minus hasn't changed much, and thus it maintains a stable pH, because the way you calculate pH is negative log of H plus. If the H plus concentration doesn't change, how could the pH change? All right, so to illustrate that point, let's try this first calculation. So here I have the nitrous acid equilibrium system here, all right, Ka is given. We have 100 milliliters of 0.1 molar nitrous acid, and we also have its conjugate base. We want to find the pH after we add 10 milliliters of HCl, but first we have to find the pH alone. So let's set up a nice table. Okay, so this is a nice table, and I am mixing two solutions together. You guys know by now that whenever you mix two solutions together, you have to recalculate what you think the initial concentration is. All right, so we got to find moles of both. right? Those are my moles. We have 100 milliliters plus 100 milliliters, so our total volume is 0.2 molar. So we're dividing, our total volume is 0.2 liters. So divide both of these by 0.2 to get our initial molarity. All right. You guys okay with that so far? Calculating initial molarity, and now I can place them into my ice table. So the HNO2 is 0.05 molar. The NO2 minus is 0.1 molar. And there's no H plus initially. We're always going to take that stance. When we start this equilibrium problem, your H plus concentration starts at 0, unless there's reason to think otherwise. All right. So in fleshing out the direction of this ice table, I have a 0 under H plus. The reaction is going to progress to the right. And then we have the Ka value is given to us. This is our setup. Let's go ahead and solve. All right, so I got 1.988 times 10 to the minus 4. Let's go 1.99 times 10 to the minus 4 for x. You guys get the same? Okay. All right, so this is this, right? Because this is a weak acid. So x equals H plus because this is a weak acid equilibrium. So I can easily find the pH by taking the negative log of that value. And so our starting pH is 3.70. How are we doing, guys? Okay, so what did we do here? This is a weak acid problem. The difference is you had to figure out initial concentrations. You have some of both the weak acid and the conjugate base present initially. Because of that, that qualifies this as what's called a buffer. This is a buffer problem. Okay? So we calculated the initial pH of 3.7. By definition, buffers do not allow the pH to change drastically. So now, this is a good spot to add a page because the next problem we're not going to have enough room for. Okay, so the next problem says, calculate the new pH after the addition of 10 milliliters of 0.1 molar HCl. Okay, so in order to do that, first I got to figure out what am I adding, right? So for HCl, I've got 0.01 liters times 0.1 molar, so it's 0.001 moles of HCl. Okay, and this is where it can kind of get tricky. Whenever you add an acid or a base to a buffer, you always need to refer back to the original number of moles that you calculated for both species. So, for example, what was the original amount of moles that we calculated for HNO2? Okay, so 0.01 moles of HNO2. and also the number of moles of the conjugate, which is 0.02 moles of NO2 minus. There are other ways to do this, but I think the way that I'm going to show you is the least confusing. Okay, so I'm rewriting what I know the initial moles to be. So my next question to you is, when I add HCl, which one of these components is going to react with that HCl? The HNO2 or the NO2 minus? Remember, a buffer has two parts, and each part neutralizes something. Which one of those two is going to neutralize H plus? NO2 minus, yes. So just, I'm going to flesh out some thoughts here. NO2 minus is going to I meant to write H plus. Neutralizes H plus. NO2 minus, being a base, is going to neutralize the acid. So doesn't it make sense then the number of moles of NO2 minus will decrease because it's being used up? So what that looks like is this. All right, let me ask you a second question. The HCl, the H plus that we add, after it's neutralized by NO2 minus, right here, HNO2 is made, right? Isn't HNO2, so doesn't our moles of HNO2 increase? There's more moles of HNO2. So what you should see then is we need to adjust our concentrations of HNO2 and NO2 minus because of this H plus that we added. One of these numbers will go up, one of these numbers will go down, and then we will recalculate what the concentrations are and plug them back into the ice table. So, what is the mole ratio between H plus and NO2 minus? One to one, right? And don't we know the moles of H plus that we're adding? Okay, so this is a little rule I'm going to write off to the side, but it's an important rule, and I will mention it frequently. Strong species react completely. Okay, and this applies always. So isn't HCl the strong species? That means all of the moles of HCl or H plus get used up. So because of that, our moles of NO2 minus are going to decrease by the number of moles of H plus that we added. So it's going to go from 0.02 moles of NO2 minus. It's going to become 0.019 moles of NO2 minus. It's a change of 0.001. It's because I added 0.001 moles of H plus, and all of the H plus that I added was neutralized, and so the number of moles of NO2 minus that I had has to go down. Okay, By the same token, didn't we say that moles of HNO2 were going to increase? Guess how much it increases by? 0.001, right? Because I had to, the moles of H plus turned NO2 minus into something, it's turned it into HNO2. So up here, 0.01 moles becomes 0.011 moles. Increase of 0.001 moles. I want to stop here before we go any further. This has to make sense before the rest of the problem will make sense. At the very beginning of this problem, we calculated the moles of the components of our buffer. We calculated the moles of the weak acid and the conjugate base, right? We did that at the very beginning. When you add an acid or a base to a buffer system, you have to identify which one of these two is going to increase and which one of these is going to go decrease. So if H plus being the strong acid, it's going to end up being neutralized by the weak base. So this one goes down, and then the product of that process is the weak acid. So this goes up. You have to understand which one is reacting and going down, which one is more, there's more being made, and which one is going up, okay? And then you adjust your moles accordingly, which is what we did right here. Right? The adjustment that you make is the moles of the acid that you add. So it's 0.001. If we added 0.002 moles of acid, then this number would be 0.018. And this number would be 0.012. You follow? Okay. All right, so now that we have neutralized the incoming acid, the next step is to calculate what the pH is by using an ice table. Right? That means we need to refigure out our concentration. So and with these ice tables, it's usually helpful because you'll be writing a series of these. Like somewhere annotate off to the side after 10 mils HCl added. All right, that way you can keep track, because you're going to get to the point where you'll have like 4 or 5 of these, and you want to know which one's which. Okay, let's figure out our concentration. So what is our total volume right now after we took the buffer and we added 10 milliliters of acid to it? Yeah, 210. So 0.21 liters. Okay, so that means our moles, each of our moles that we have has to be redivided by that volume. So up here, divided by 0.21 liters. Here, divided by 0.21 liters. .0524 molar. 0.0905 molar. Okay. We have our initial concentration, our new initial concentrations. So we will plug them in. And the way that we calculate these, because we have completely reacted the strongest species, we reset the H plus concentration to be 0. Okay, we reset it because we're starting from, the beginning, the initial moles. And whenever we react them completely, the assumption is that there is no H plus until this goes forward. All right, so plus, do what you do like you normally do now. Oops, my bad, that's minus. Minus x here, plus x here, plus x here. Ka, this is still the same. It's the same acid, right? So our Ka was 4 times 10 to the minus 4. So I get x to be 2.3 times 10 to the minus 4. And that means a pH of 3.64. Let's stop and think. What was the starting pH of this buffer before we added anything? 3.7. And we added some acid. Now, whenever you add acid, the pH should go down. In this case, the pH did go down, but by only a little amount. It went from 3.7, 3.64. So a buffer resists pH change. It doesn't mean there's absolutely no change. It just means the change is greatly minimized. If we added 10 milliliters of acid to water, the pH would change by several pH units. Guys, like it would go from like 7 to like 3, right? Here it went from 3.7 to 3.6. That is the purpose of a buffer, to minimize the change. And it can all be calculated using ice tables and a little bit of stoichiometry. So imagine progressively adding more and more and more acid to this system. Can you imagine that your pH would go 3.6, 4, 3.58, 3.50, 3.47? Can you imagine that? Incremental changes, right? That's what's going to happen. And that is why on a titration curve, in the titration curve, there's an area where the pH barely changes. It's changing, but not drastically, right? That's because at that part of a titration curve, that's what we call the buffered region. Here and here. The non-jump, right? The plateau, the flat part. That's what we call a buffered region. And that's what's happening during that flat part. Okay. The next question asks, we're using the same system, the same buffer, but this time we're going to add a base and we're going to see what happens. Okay, so calculate the pH after the addition of 10 milliliters of 0.1 molar sodium hydroxide. Okay, so in order to do this, we need to rewrite what our initial moles were. So our initial moles of, we had 0.01 moles of HNO2. And we had 0.02 moles of NO2 minus, right? This is what we had at the beginning. And what are we adding? We are adding base. 0.01 liters times 0.1 molar. So again, 0.001 moles, but this time it's base. I have a buffered system. I am adding hydroxide. Which one of these two species will neutralize the incoming hydroxide? HNO2, the weak acid. Okay? So it neutralizes the OH minus, and the moles of it are expected to decrease. The NO2 minus moles will increase because that is a product of the neutralization. What does a neutralization reaction look like? It is this. So let's figure out how many moles we have now. The amount of change is the number of moles of the OH minus or H plus that you added. So what is my new number of moles for HNO2? HNO2 now becomes what? This guy. What's the new value? Well, are we increasing or decreasing it? Decreasing it. And by what number? The number is actually on the screen. By 0.001. Therefore, 0.01 minus 0.001 becomes 0.009 moles of HNO2. That is how many moles we now have. 0.009. Okay. The moles of NO2 we expect to increase. It's going to be 0.021 moles of NO2 minus. What is our total volume currently? $210. All right, so our molarity, let's work out our ice table here. We need new initial concentrations. So 0.021 moles over 0.21. Oh, that's just 0.1 molar. So that's our HNO2. Our 0.009, oops, sorry, I have that wrong place. That's here, 0.1 molar. Our HNO2 is 0.09 divided by 0.21 liters. It's going to be 0.0429. And we work it like we do. Find the new pH. It's the same system, so it's the same Ka. Did you guys get 1.7 10 to the negative 4? Okay. That means the pH is the negative log of the H+, and so we get about 3.77 for our pH. Does that make sense? What did we add? Base. Therefore, we expect the pH to change how? To go up. A lot or a little? Just a little, and it did. This is how we solve buffer problems. There's equilibrium involved, right? There's some adjustments to the moles that you need to make with the understanding that strong acids and strong bases, you have to use it all up. And then whatever's left, you recalculate the concentration and plug it into an ice table. And that is how you find the pH. And that is a long enough lecture. So...